Hello and welcome to the Strength of Material online lecture series of Mechanical Force and of BTech MDU syllabus. I'm Imran Siraj and I'm teaching you since past six lectures. Today's seventh lecture. I hope all the concepts that I have given you are clear. And right now we are entering into the crucial stage of this strength of material. This is basically the most important topic of strength of material, and this is the crucial point from where we have to start the analysis of beams and structures. So this is the real part, and this is the analytical part, and this is the implemented part of strength of material. Earlier we were talking about the preface, the materials, the response of the materials, the basic qualities, and the basic definitions along with their reactions. So we were talking about those things. From today onwards, we'll be talking about the real application or real uh, analysis of beams and columns, etc. So you can see here now you can see my screen. So today, yesterday, in our last topic, we studied about the bending. We studied about the types of beams and types of loadings. What are the beams? How they are loaded, and at the same time, we discussed about the reactions. What are their reactions? And same times we discussed about the types of beams and loadings. So today we'll be implementing the type of beams and loadings, and we'll be advancing into the stage where we have to study the shear force and bending moment diagram. So first of all, we must be knowing what is a force. As I earlier told, that force, that shear is a process of tearing. So we discussed in the second lecture or first lecture also that shear is the process of tearing. We have to tear apart if any forces, if any two opposite forces acting on the surface of the objects are so that they are tearing apart the body. They tend to tear apart the body. The stress is known as shear stress. Similarly, the force, those are acting parallel to the surface and in opposite direction, and their resultant is tearing of the body. So these forces also known as shear force. And bending moment, as we know, moment is the product of force multiplied by force at perpendicular distance. Bending is the uh, effect of the moment of the couple moment is such that it's bending the beam. So bending moment called bending moment. Shear force are the forces that try to tear off the body and are acting on the surface and are acting in the opposite direction. And bending moment is the moment because of which the beam is such that it tends to bend. So this was shear force and bending moment. Now come to the shear force. Net vertical force or unbalanced vertical force on either side of the section. This may be defined as, because if we are having two forces, equal and opposite forces trying to tear off. So if we check every cross section of the beam, we'll find that not all the cross sections are equally loaded. There are certain on sections there are forces, on sections there are forces that are not balanced. So these forces are known as shear forces, and they try to get the beam tear off into parts. So this is the shear force, net vertical force or unbalanced vertical force on either side of the section. Now we'll be giving like this. You can see here this is an example. This is the body, and in which two forces are acting superficial to the superficially on the surface of this body. So one is in a direction, in upward direction, another is downward direction. Like here we have the example. This is the beam, and this beam is supported by column. So this way the upward force is acted by the column, and on the beam we have loading. So the clear span or the part where the beam is not there. So uh, beam, the force that is that the force that is vertically applying by the column is this much, and at the same time there is there is a load on the beam downwards, that's acting downwards. So these are two parallel and opposite forces, and these two are trying to tear off this body. So this is called shear force. Now come to the sign convention. Sign convention, if we take if we take any section of any column, and if we see that the force is acting upwards in the left direction, so it will be positive shear force. Whereas if the force acting on the right in downwards direction in the right section, it is known as negative shear force. Let me come to this picture and let me show. You can see here, if the force is acting upwards in the left section of the column, if the force is acting upwards in the left section of the column, this is known as positive shear force. Or vice versa, if in the right hand direction, if in the right section of the beam, in the right section of the beam, the force is acting downwards, it is known as positive shear force. And the vice versa is also true. If the in the left section of the beam, the force is acting downwards, or in the right section, the force is acting upward direction, this is negative shear force. So shear force is quite easy and quite simple. If you can check only one thing, you can keep in mind only one thing, is that we have to check the left portion. If it is upwards in left portion, then it is positive shear force. Or if there are no clear indication on the left portion, then we'll go to right part, and we'll check whether the force acting downward, it's positive shear force, or the vice versa is also true. If we find in the left section that force is acting downwards, and or right in the right portion the force is acting upwards, so this is known as negative shear force. This is quite simple and quite clear, I hope. Now this is sign convention for the shear force. This is left one is positive, and again if it's acting rightward, positive, then if it acting downward in the left section, this is negative. Okay, now I told the bending moment is a type of movement in which bending moment is a type of movement that tries to bend the beam. So moment, as we know, moment is a product of force multiplied by perpendicular distance. So let me check. Let me tell about the sign convention. So we see there are two types of sign convention. If the beam is bent such that its complex or belly or stomach is downwards, it is positive shear stress, and this condition is known as sagging. Sagging, like we see in our homes, that we have a wire on which we uh, put our clothes to dry in the sun. So like that, if the wire comes down, so we see the wire is bulging downwards, and then the wire or rope is bulging downwards, it is known as sagging. And the reverse is the case, hogging, it is known as hogging, and the convex of the stomach or center point comes up, and this is known as hogging, and then the bending moment is taken as negative. So it's also very simple. We have to keep in mind just one thing, that if it's sagging, that means convex is down to facing towards the earth, facing beneath, then it is known as hogging, sagging, and the opposite direction is known as sagging, hogging. So you see, so in the sagging, the internal part or the upper part is compressed, whereas the lower part or the lower face is under tension. So lower face expands and the upper face compress. Similarly, uh, in the hogging, In the tension, the upper face is in the tension and it expands, whereas the lower part or the lower surface is under compression and contracts. So these are two sign convention of bending moments, sagging and hugging. For sagging, it's positive. For hugging, it's negative. Okay. Now, these are two shown. You can see these are sagging, positive bending moment, then negative bending moment. Okay. Now, we'll study the first beam. We talked about the types of beams that we have studied, and at the same time we studied about the type of loading. So cantilever beam, as I told, is a beam that is supported only at one end. The other end is the free. So here we are having this type of support. We are having a cantilever beam that has one end supported and another free. So we will analyze first of all cantilever beam. We will draw bending moment diagram and shear force diagram of cantilever beam. So you can see we have a beam that is supported at one end and free at another end. And the length of span is L. Then point force P is acting downwards at free end. Force P is acting downwards at point B. A point load P is acting downwards at free end B, and there is no other load except this P, and this is supported at fixed end, that is supported from beneath, that is reaction R A B at point A. So this reaction basically will have combination of reaction. One is vertical upwards, another is horizontal upwards. I told that when this is the condition, the reaction of the force is inclined. The reaction of the hinges, reaction of the rigid end is inclined. So basically this inclined has two components. One is horizontal and another is vertical. But in case here the beam is loading from upwards, from beam is loaded vertical, beam is loaded in vertical direction only. There is no horizontal forces. So this way, this horizontal component will have not any effect, and it is neutralized, and only effect that has is vertical effect, since we have all the forces, since we have force P that is acting vertically downwards. So this is force, and moment will be acting like this. Moment is acting like this because this is trying to bend in this direction only. So P, as we know, moment is force multiplied by perpendicular distance. So first let's draw and understand the shear force diagram, then only we will come to the bending moment diagram. This is what I was telling about. We have a cantilever beam of length L, fixed support at A and B is free end, and then we have point load P at free end. This is we have to find. So this is the way of finding ma. This is the way of finding shear force and bending moment. So as I told, horizontal component of R is 0, fixed we know, since the beam is under equilibrium, so all the vertical and horizontal components must neutralize each other, so that we can say sigma fx is equal to 0, sigma r h is equal to 0. So as there is no other horizontal force, then we know RH is equal to 0. In my last slide, I told that you can see RH has no balancing force, so that is 0. This will not affect at all. And similarly, sigma fx is also 0. Sigma fx also 0. There are no horizontal loading of the beam for time being. We'll take later on, at the later stage, we'll be calculating. When we'll calculating fix the shear force and bending moment diagram of beams, we'll have many problems where we have to face the horizontal forces as well. But right now, for the basic concept, basic step, we are not considering any horizontal force, only vertical forces are there. So this way we can find uh, RH is equal to 0, and RAV must be equal to P, because there are only two forces, one is acting downwards and one is acting upwards. So R uh, vertical component of R acting at A is RAV must be equal to upwards and P must be downwards. So RAV must be equal to P, number one. Number two, bending moment starts from here. So P into this much length, this much length, this much length, this much length. If we take any point or any cross section, we will be find bending moment will be P multiplied by force multiplied by perpendicular distance. So if we take this point, any point, say 1 meter from the end B, so we'll have P into 1, then we take 2 meter, P into 2, then we take P into 3, then we take 4, P into 4, and so on and so forth. And this will be end at P A point, P into L, because A to B is the whole length, L given in meters. So L is the length of the span. So at point A, we will be having moment P into L. P force multiplied by whole distance. Why we are taking P into L? Because I told perpendicular moment is force multiplied by perpendicular distance, and you can see the this is the free end and this is the supported end. So the beam will be coming slightly downwards because of this loading. B is free end and there is no support from beneath. So the P force will deflect the beam at free end B down vertical downwards. So this will be vertical downwards at B point, and we will discuss about this point later on. But right now we have come to the conclusion that moment is P into L, RA0, RAV is equal to P. Now come to the shear force diagram. How this shear force diagram is drawn, you can see what I was discussing about. If we take any cross section x at a distance of a small x, so we'll find the moment P into x. Now this is the shear force diagram and bending moment diagram. What are these and how will they act? First of all, I told that when you are drawing shear force diagram, take the right section, take the left section and find whether the force is acting upwards or not. So if we take any section, on this beam, say we have taken this section, and what we'll find, we'll see that on the left of the section, there is only one force, that is R. There is only one force, that is reaction, that is acting vertical upwards. So when this vertical reaction, this acting upwards, only force is there on the left section. As I told, the sign convention was that whether we have to check the left section first of all. If the bending is the force is acting vertical upwards, the shear force is positive. So this is the case. You can see we have only one force R acting vertical upwards on the left section of the beam. So that means first thing is that shear force is positive, number one. Number two, we know reaction R is equal to P. So either we take R or P, it is the same. But since P is always given, R you have to calculate. So you have to take the P. So if P is given, P will be given to you for in order to solve the problem. If P is given, so you have to take the P is equal to R. So now draw a line AB, draw a line. This is shear force diagram. Draw a line AB and assume a suitable scale. For example, this P is given as 10 Newton or 10 kilonewton. So you can assume 1 kilonewton is equal to 1 millimeter, and this way 10 Newton is equal to 10 millimeter. So from here you just measure a distance 10 mm and you will find this point P. This point P, you have taken 10 millimeter from beneath in order to draw a shear force diagram. So you come this point. Now you will see that P is acting, P is 10 Newton. So you have drawn at point P 10 centimeters, because I told you take a suitable scale, 10 millimeters, sorry, 1 centimeter. So you can take a suitable scale. So you have taken suitable scale, 1 Newton is equal to 1 millimeter. So this way 10 Newton will be representing 10 millimeters. So this way we have found 10 millimeter. Now we've got point P. Okay. Now come to this whole beam. There is no other force except P, and at the end you will find a reaction that is only because of P. So from here to here, no other force is acting except P. So what we'll take, what we have concluded, that 10 Newton force will be acting from here up till here, from here up till here, all the way. This only 10 Newton force is acting. There is no other one to challenge this except the end. At end, this is only vertical upwards. So what I will do, I will take another 10 mm at the left hand side also. So you will ask why I have taken this, not downwards. I will clarify that only force acting from here to here, from B to A, along the span of the beam is 10 Newton. So I have taken 10 Newton, and shear force diagram, I told the sign is positive. So from here to here, we have found 10 millimeter here, 10 millimeter here. Joining these two points, we'll have this diagram. And this is positive because shear force diagram is positive if the left section of the beam having a force of vertical upwards. So this is the case. So we have got shear force diagram positive and vertical upwards. Number one. But our exercise is not complete because we have only determined shear force diagram, shear force, and not we have determined bending moment diagram. So for that we have to come to bending moment diagram. So bending moment, as I told, is a moment, and moment is always taken force multiplied by perpendicular distance. So you can see this is the free end. So when this is free end, this free end will be is not supported at point B. So the beam will be coming vertical downwards. So beam will be coming vertical downwards. This way the beam will forming a shape of hogging. That means the upward face, the upward convex will be upper side. So the center of the beam will try to move in the upper direction, upwards. So this is the case of hogging, and hogging is negative bending moment. So we have applied force B at the end B, and we'll start taking moment from here to here. So at this point the moment will be 0 because P into perpendicular distance 0. P is force P is passing point, force P is passing through the point B. So there is no vertical distance, there is no perpendicular distance. That's why P into 0, then P into 1, P into 2, P into 3, P into 4, P into 5, up to P into L. So the maximum bending moment is at this point P into L. So what we have done, we have taken at B 0 point, we have drawn a line, baseline AB, and all we know that the shear force, that the bending moment is negative. So we have taken point B, and at the point B it is 0. So this is 0. So we take this point. So you come 0, it starts decreasing, 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 up till point A. At the point A, we have bending moment as P into L, and say this P is 10 Newton and L is 5 meters, length is 5 meters. So we'll have P into L, that is 10 into 5, 50 Newton meter. So we'll represent 50 Newton meter accordingly, and we have assumed 1 Newton meter is equal to 1 millimeter. So we have taken this as 50, a line 50 vertical line from A to B, that is perpendicular to AB, that is 50 millimeter, and we will join point B to point this P. And this is a straight line because only force that is acting from here to here is P, and because of this we have a shear force, negative shear force, that is coming from 0 to P into L, that is 50 Newton meter. So This is the shear force diagram, that is positive, and again this is the bending moment diagram, that is negative. I hope it's clear to you now. Now we will take another beam. This was the case of cantilever beam. Now we'll take cantilever beam, another type of loading. So this is, again we can see this is a cantilever beam, and this is uniformly distributed load. Uniformly distributed load, that means there is no point load, only load is uniformly distributed all along the span of the beam. So this is uniformly distributed load, and uniformly distributed load is given as per meter or per unit length. So we have seen it is given as W kilonewton per meter, W kilonewton per meter, and as the L is the length in meters. So the total force that will be acting will W into L, and at the center point. If we have to replace the uniformly distributed load into point load, then we will take uniformly distributed load W multiplied by length of span W into L, and that is acting exactly at the center of the beam. So this will be acting at this point, and the beam again will be slightly deflected down, slightly bending downwards. So again we will see that shear force diagram. First of all, shear force diagram, and we'll see shear force diagram is again the direction of the resultant or the force that is acting in the left section is upwards. So this will find that reaction R will be upwards, and the because you can see the force is acting here. So this is acting here, W into L, and the reaction will be W, reaction RAV will be W into L. So the force will be acting vertical upwards, and again bending moment will, sorry, shear force will be positive. Similarly, the case will be bending moment. Bending moment will again be negative. In case of shear force diagram of cantilever beam, we have seen that in both the cases, in point loading and uniformly distributed loading, we have got the shear force positive and bending moment negative. So check this. This is again bending moment, the point, another point that I have discussed, forgot to discuss, the point load. This uniformly distributed load is converted into point load, and this point load is acting at this center of the point. So the bending moment will be W into L. W into L, this is the force, W into L, and the length by which we have to multiply in order to get bending moment is L by 2. So the bending moment will be W L into L by 2. This way you can see the bending moment is W into L by 2, and we have got bending moment of WL square by 2. So this way you can see this is the bending shear force and bending moment diagram. Now within 2 minutes I conclude that we have got a shear force positive as I told earlier, and bending moment negative. So shear force we can see when we have converted this uniformly distributed load into point load, we have got a point load at the center of the beam. So for this a point load that's acting at the center of the beam, we don't have any loading at this point. So the free end B doesn't bear any load, and the point A, the extreme point A, will have maximum load, and that is W into L. So we start from zero. You see, as I told, the shear force will be positive. We start from zero. This will keep on increasing up till W into L. So W into L is the maximum force that we have taken. It's the maximum force that is acting on this beam, and this is the shear force, positive shear force, and starting from zero up till maximum, and maximum is W into L, because vertical reaction will be equal to this downward force, that is W into L. Now come to the bending moment, you will see bending moment starts from here, zero force, zero distance, and it keep on decreasing, 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 decreasing up till we get WL square by 2. Because I told this is the case of hogging, so in case of hogging, bending moment is negative. So we have taken all the bending moment is negative, and why this is straight line and this is curvilinear, and this is why this curve is given. So we can see that at this point the load is zero, the load is keep on increasing, increasing, increasing up till this point. So the load is increasing, 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 increasing up till this point. But you can see this is a quadratic equation. Bending moment, we have got quadratic equation, WL square by 2. So you can see here, so this way Wx square by 2. Bending moment is W into x square by 2 for that particular section, and this way WL square by 2. So this is a quadratic equation. So quadratic equation, the curve assigned with the quadratic equation will be WL square by 2, and this way this is a parabolic curve, and parabolic curve is there. So this curve is there. Okay, I hope the bending moment diagram and shear force diagram concepts are clear to you. Thank you for watching, and okay, bye.